Okay, I'm going to try to take the area under the curve, 3x plus 7x, from -1 to 4 using rectangles. And the rectangle method is also known as the riemannsum method. If I take a look at some parabola, this could be a representation of that parabola. If I want to take the area under the curve from -1 to 4, it will add up all the areas. Could be something like that, could be all positive. In this case, it probably will be all positive. We're adding up the areas under the curves using rectangles, starting from -1 and going to 4. Now the area of a rectangle is going to be the height of the function at any given point times the width of that rectangle. So I need to figure out what the width of the rectangle is going to be. How do I get the width of the rectangle? I could take 4 minus the -1 over the total number of rectangles I'm going to have. That is hopefully 5 over n. How am I doing so far? Excellent. Now I need a representation for xi. Now since I'm going to use right-hand rectangles, I'm going to start with my first left endpoint, and I'm going to add the width to find the first piece. Now, I want the limit as n approaches infinity of the sum from I equals 1 to n. The sum from I equals 1 to n just represents the sum of all the rectangles. The limit as n approaches infinity means I'm going to take an infinite number of rectangles, and I'm going to add them all up. I would take an infinite number of rectangles because it is 100% accurate. I'm not estimating at all. I'm taking an infinite little slices. I'm going to replace my f of xi times delta x as all the little rectangles, heights, and widths. The limit as n approaches infinity from the sum I equals 1 to n. My f of xi is going to be 3. My xi is -1 plus 5i over n squared plus 7 times -1 5i over n. That is my f of xi. I'm going to times it by my delta x, which is 5 over n. We're doing good so far? Now I need to multiply some of this stuff out. Hopefully our algebra isn't too bad. We'll see how mine is. -1 times -1. How am I doing so far? Continue with my algebraic, collecting like terms. I'll multiply the 3 through. Over I squared n minus 7 plus 35i over n, all times by 5 over n. Yes. This should be over n squared. I missed an n squared there. Perfect. Reverse fit's good. Next step, I'm going to multiply through my delta x through after I collect my like terms. I'm going to have -4 times 5, -20 over n. Put those together. 5 times 5, 25I over n squared. And what did we figure out 5 times 75 was? 375. I squared over n cubed. Next step, split them apart into individual sums, factoring out the pieces that aren't i's. So I've factored out everything that wasn't an I of all those pieces, and I replaced those sigmas with the table I gave you in your notes. Unfortunately, they're still burned in my memory from when I used to have to do this. I'm going to take the limits to infinity. I can use the shortcut in this case because a lot of teachers don't feel like we have to be repunished by multiplying the top by the reciprocal 1 over the highest power on the bottom. We can avoid that. First case, I just got 20. Second case, 25 over 2. Third case, 375 over 3. And what do we get for an answer? What do we get? 117.5. Now, is there another method we could use to solve this? Absolutely. I can take the integral from -1 to 4 of 3x squared plus 7x. Once again, height of the function. Dx is the width of the function. We're doing quite well. The integral of 3x squared is x cubed. The integral of 7x squared, 7 over 2, evaluated at -1 to 4. 4 cubed plus 7 times 16 over 2 minus -1 cubed plus 7 over 2. I'm hoping that it's still 117.5. If we're still not 100% satisfied with that, we could type it into our calculator. 3x squared plus 7x. Go down to my integrate function. I'm going to find the integral from -1 to 4. And I got 117.5.